Well, hello, and welcome to this lecture about capacitors and capacitance. This is a Physics 2 class, and we are going into the basics of electric capacitors and capacitance. So what is an actual capacitor? It's a device consisting of two oppositely charged conductors that are close to one another, and the goal of a capacitor is to store charge. This chapter follows after the electric potential energy chapter, namely the chapters on voltage. And the idea is that a capacitor stores charge. And it's basically the practical device that does so. Usually a capacitor, at least for the sake of this class and most simply, consists of two parallel plates that are connected to a voltage source like a battery. When the switch is closed, the capacitor over time charges and the plates become equally and oppositely charged. Notice that here we have a battery depicted as a real battery, and it has a voltage source. And notice that here is a switch, which we can close the switch or open the switch to allow charge to be moved from one capacitor to one capacitor plate to the other side of the capacitor plate. But the idea is that if we take electrons away from the positive plate, we put them on the negative side of the capacitor, and each of these plates will have the same magnitude charge on them, but the positive side will have a deficiency of electrons, the negative plate will have a surplus of electrons, and there will be an electric field set up between the plates of the capacitor. Okay. Now, we often in this class model capacitors as parallel plates, but in general, more sophisticated geometries are true, but we won't study that much in this class. Now, if there is a parallel plate capacitor, there's a couple ways to sort of look at this. One way to look at this is a V versus X graph, or in this case depicted as S. Okay, and S is sort of an axis going from the negative plate towards the positive plate. Notice that as we go from the negative plate towards the positive plate, the voltage goes up because by convention, the negative plate is at a lower voltage than the positive plate. Notice that we can say if the negative plate is at 0 volts and the positive plate is at 1.5 volts, there should be a nice linear increase of voltage with distance from the negative plate to the positive plate. Note that each conducting surface is an equipotential surface having a constant voltage, but notice that there will be planes which are constant voltage parallel to the plates of the capacitor. Another way to depict this is not with a graph or with sort of three-dimensional planes, but in a single top-down view where each plate is shown here and then dashed equipotential lines are shown. And then a third way even to define that is to show maybe voltage on a surface, and then S is between the plates, but then as you go side to side, that shows the width of the plate. Okay, so there's lots of ways: potential graph, equipotential surfaces, contour map, or an elevation graph. Okay, how can we actually measure the capacitor's ability to store charge? This is the notion of capacitance. Capacitance is always a positive quantity, and we'll use the symbol capital C for capacitance. And that's going to be Q divided by delta V, where Q is the total charge on the capacitor, that's in units of coulombs, and delta V is the electric potential difference between the capacitor plates, that's in volts. Now, by the way, Q being the total charge on the capacitor, you could think of that as the magnitude of the charge on one plate or the other, because if you add up the charge on both plates of the parallel plate capacitor, it actually sums to 0. So sort of the total charge in the capacitor is really the total charge that gets separated. Now note the units of capacitance are going to be a new unit that has not been discussed yet in this class. 1 coulomb, SI units of charge, divided by 1 volt, we give a new name, and that we call farads. Capital F, a farad is 1 coulomb per 1 volt. Farads is named after the Scottish physicist Michael Faraday, whom we will certainly discuss more in this class. So, moving on from there, 1 farad would be an enormous capacitance. Typical capacitors have capacitances in the picofarad to millifarad range. So that's 10 to the minus 12 farads to 10 to the minus 3 farads. In fact, the most common range of capacitor values that I've seen is in the microfarad range. So that would be on the order of 10 to the minus 6 farads. Now the question is, what are applications you could think of capacitors? Hopefully you can think of many. Hopefully you can think of many electronic devices that store charge. And you release them at a time that you're interested in finding that. So here's a couple examples. Capacitors are important in electric circuits, and they come in a variety of sizes and shapes. One example is a time delay circuit. Okay, so anytime we need to delay something but then send charge at the moment we're interested, then that's going to be a time delay circuit. A defibrillator. A defibrillator is going to put an electric shock across a patient's heart, and then hopefully their heart will restart. That's a medical application. And it turns out the keys on most computer keyboards are capacitor switches. When you press the key, you push 2 capacitor plates closer together, increasing the capacitance, and that allows a signal to be generated. So let's say more about a parallel plate capacitor, in particular the geometry of how one would build it. Suppose we have a parallel plate capacitor that has plates which have area A and has charge positive Q on the positive plate, negative Q on the negative plate, and the plates are separated by a distance d. Let's let the capacitor plates be very thin. So you can derive the capacitance, okay? Now the capacitance can be derived in a certain way. I'm not going to show it, but it basically has to do with that we know surface charge density from a conductor is like sigma divided by, has to do with sigma and epsilon. And we also know that the voltage between 2 plates is electric field times the distance between the plates. And if we work that out, we should be able to get this equation. So epsilon naught we know to be the permittivity of free space, A is the area of the plates, and then D is the distance between them. Okay? So notice, if you're building a parallel plate capacitor, the larger the area, the greater the extent that you could put charge onto the plates, so that should increase the capacitance. But the closer distance the plates are to one another, the greater the capacitance, because there should be a lot of energy stored when charges are close together but not allowed to come together. By the way, notice epsilon naught assumes that what's inside the capacitor is perfect vacuum. We will relax that constraint at the end of this lecture. Now, by the way, again, this equation is the capacitance equation when you build a parallel plate capacitor. The previous equation for capacitance was the definition of capacitance. Note that between 2 parallel plates, the electric field is nearly uniform. And notice that there are edge effects. But for the sake of this class, we ignore those edge effects. They can actually get quite complicated, so we won't get to that level of complexity. And there are other arrangements where capacitance does not depend upon things you might think it would. Okay? So again, we're not getting into other complicated geometries in this class, but we move on. So I will come back to this parallel plate capacitance example when I do the example problems lecture videos. Now, for the sake of this Calculus-based Physics 2 class, I would like to define circuit symbols, a few of which we've already seen thus far in the class, but several we will see a little bit later. And a circuit diagram is a simplified representation of an actual circuit. Instead of drawing actual batteries and instead of drawing actual capacitors, what they look like and things like that, it's easier to just use the somewhat universal symbols. These symbols aren't entirely universal, but they certainly are pretty common. So notice that the ground symbol goes from long to shorter lines. Think about that the charge is sort of going into the earth and more or less stops, because the earth can receive enormous amounts of charge, or it can give enormous amounts of charge. Notice the capacitor symbol is what you might expect. It looks like two parallel plates. So that's the capacitor symbol. Note the battery symbol. The battery symbol looks somewhat like a capacitor because a capacitor and a battery both have a voltage and stored charge. But a battery provides a constant voltage, whereas a capacitor does not. I'll say more about that as we go along. But a battery symbol is typically a long line with a short line right after it with a space in between, and the positive side is the long line and the short line is the negative terminal of the battery. By the way, sometimes you see long, short, but the long side is still the positive side and the short, which meets the wire, is the negative side. Okay. By the way, I didn't mention this, but these pieces that come out of the electronic devices, those are wire, and assume that those pieces of wire are conductor wrapped in insulator. For the sake of this class, unless otherwise told, assume that pieces of wire are perfect conductors, but we will at times relax that assumption, but not often. Here is the symbol for a switch. You can close the switch and allow charge to move. You can open the switch and disrupt the flow of charge. Here's the symbol for a resistor. And a resistor is kind of like a heartbeat symbol, sort of a squiggle. We will talk about those a lot in chapter 9 and 10 of this class. Whereas a light bulb is sometimes represented by the resistor symbol. In fact, it generally just can be. But sometimes it's given sort of this bulb-looking symbol. But a light bulb is still a resistor. Here is a junction. A junction is a split in a piece of wire. Allows charge to move in multiple directions. And lastly, not until we get to chapters 11 and 12 will we get this symbol of an inductor. An inductor kind of looks like a helix. We'll talk about that more later. Most of the symbols will be actually introduced in chapter 9 and 10. We'll stay with the capacitor and the battery symbol in this chapter, in this lecture. I already mentioned that lines are used to represent wires, and that if one closes a switch, charge flows on that line. Okay? A battery's positive terminal is a longer line, and by convention, the electric current, which we'll define, goes from in positive to negative direction. Again, I'll say more about that as we go along. Okay, now I want to discuss arrangements of capacitors, namely when you have more than one capacitor. What does it look like to arrange them and either store more charge or less charge, or set the capacitance or set the entire charge of the circuit? Okay? So note that if we have capacitors in parallel, imagine parallel means separate branches, or you could think like the rungs of a ladder. They're parallel to each other. The capacitor plates have the same voltage across them as the voltage of the battery, or for that matter, the voltage source. Let's think about why that is. Notice that the positive terminal of the battery is connected to the left-hand side, if you will, of both capacitors 1 and 2 here, whereas the negative terminal of the battery is connected to the right-hand side of each capacitor. If the battery, the voltage source, acts like a pump, or basically a source of electric potential energy, it should make sense to you that there's a free path for charge to charge each capacitor to the same voltage, to the same electric potential energy per unit charge. Okay? So that is going to be the same in a parallel arrangement. Now, in general, capacitance 1 and capacitance 2, C1, C2, capacitance is always going to be a capital C. In general, they can be different. So since they're different, each can store its own amount of charge, and that amount of charge is going to depend upon the capacitance. The circuit diagram will look like so. The same delta V is across each of these, but Q1 is the charge on capacitor 1 and Q2 is the charge on capacitor 2. If you add these capacitors up, they would sort of add together and act like a single capacitor. When we add capacitors up, what we do is we calculate what we call the equivalent capacitance. That's the capacitance as if the entire setup of multiple capacitors acted like a single capacitor. Notice, because each branch acts independently, having the same voltage, the total charge is just going to be the sum of the charges of each of the branches, namely in this case Q1 plus Q2. And the total capacitance for capacitors in parallel is just going to be the sum of the individual capacitances. So it's going to be C1 plus C2 plus all the way up to C capital N, where there's capital N, that's an integer, the maximum integer, number of capacitors. Notice that the equivalent capacitance is going to be greater than each of the individual capacitors. Sure, that's because the overall capacitance is going to be a sum. So even if we have a lot of small capacitors and one very large one, the overall capacitance will be larger than the largest one. Hopefully this is pretty straightforward. Now, capacitors in series, I think, get a little more difficult to understand. Notice that capacitors that are in series are sequentially added. So they're one right after the other. That's what we mean to be in series. What is the same on each of these capacitors is the charge, not the voltage, but the charge. Let's think about why this is. The positive terminal of the battery is connected to the left-hand side of capacitor 1, but the negative terminal of the battery is connected to the right-hand side of capacitor 2. Notice that if we build up a charge, let's call it positive Q, on the left-hand side of capacitor 1, there must be charge negative Q built up on the right-hand side of capacitor 1. But by polarization, that means we must build up positive Q charge on the left-hand side of capacitor 2 and charge negative Q on the right-hand side of capacitor 2. And notice that because these are conductors, and by polarization and induction of charge, we must have the same charge on each of the capacitor plates. Now, what that means is the charge will be the same on each of these capacitors. But what that also means is the voltage will be different across each of these capacitors depending upon each thing's capacitance. So here's what the circuit diagram looks like. These are two capacitors sequentially. Notice that they're labeled C1 and C2, but they have delta V1 and delta V2. Now, unlike charges adding up to the total charge, we are going to add the capacitors together to get a single capacitor that's series capacitance, and this is the equivalent capacitance in series. But notice the delta V of both of these capacitors will be the delta V of the battery. So notice the delta V of the battery total is delta V1 plus delta V2. Notice that the total sum of all the voltages is the total voltage of the voltage source. But how about the total capacitance for capacitors in series? You have to sum the reciprocal capacitances and then in fact actually take the reciprocal so to get the equivalent capacitance. So the equivalent capacitance, 1 over it in fact, is equal to 1 over C1 plus 1 over C2 plus ... all the way over to 1 over Cn. And notice that this actually leads to a very important rule, that the equivalent capacitance for capacitors in series will always be smaller than the smallest one. In other words, the equivalent capacitance is smaller capacitance than any of the individual capacitors. That is to say, you're actually going to store less charge if you have capacitors arranged, the same two capacitors arranged in series as opposed to being in parallel. Okay? But the voltages will add together to be the total voltage of the battery or whatever. Okay, so I will perform this example in the example video. And then I also want to talk about the energy stored in capacitors. Since capacitors store charge, the stored charge can be used as electrical energy. To find the stored energy, consider the work done in moving a charge dq from one plate to the next. So if you recall, the work done to move charge from one plate to the next is Q times delta V. But if it's a small amount of work and the voltage is constant across the capacitor plates, there's a little bit of charge, an infinitesimal amount dQ. But we know that delta V is Q over C from the definition of capacitance. Notice this is an equation we can integrate because we can integrate work and we can integrate Q dQ, and that's like integrating x dx as an antiderivative. So that should be Q squared divided by 2. So if we integrate, we should get Q squared divided by 2, and there's a C downstairs. So notice that the electric potential energy stored by a capacitor, this has units of joules, is going to be the total charge on the capacitor, that is on the positive plate or negative plate, the magnitude, squared divided by 2C, C being the capacitance. Now notice, you can make this into different versions of the equation. Notice this form of the electric potential energy stored on a capacitor is going to be most useful if you know the charge and you know the capacitance. But suppose we don't know that. Suppose instead we know the voltage across the plates and the charge. Well, capacitance is Q over delta V. So 1 over capacitance should be delta V over Q. So one of the Q's goes away, you get a delta V, and you get a 1/2. So 1/2 Q delta V is also the electric potential energy stored by a capacitor. And then finally, what if you don't know the charge? What if in fact you know just the capacitance and the voltage? This is actually pretty common. So we know that Q right here is equal to C delta V. So if I plug that in, I should get C squared delta V squared. So one of the C's cancels, we get 1/2 C delta V squared. So notice this is sort of like cyclic versions of the equations. Use the version of the equation which is most convenient for your situation. In fact, I would choose a version of the equation if you're comparing things where one thing stays constant and another thing you know about changes. Okay? And it turns out this last expression, 1/2 C delta V squared, can be used to find what's called the volume energy density of the electric field. So you can find the energy per volume, that's in joules per meter cubed, and that's this equation, 1/2 epsilon naught E squared. And notice that the symbol is lowercase u subscript e, meaning energy per volume. The subscript capital E means in the electric field. And notice that we can use the definition of capacitance and the parallel plate capacitor stuff to kind of get to this equation. Now, by the way, even though this is derived from a capacitor, this is actually a valid equation, volume energy density for an electric field in any situation. By the way, this is the volume energy density in a vacuum. That's because we have epsilon naught, but that's going to be true in general as long as we're in a vacuum. Now, the equations on the previous slide apply to a capacitor of any geometry. The energy stored increases as the charge increases and as the potential difference increases. That should make sense to you. The more charge you put on a capacitor, the greater energy it stores, and the greater the potential difference, the greater the voltage, you should also get greater energy stored in the capacitor. But in practice, there is a maximum voltage before a discharge occurs between the plates. The energy can be considered as if it were stored in the electric field. Here's another example problem. I will do this in an upcoming video. Last thing I want to talk about is, what if we relax that condition that there must be vacuum in between the capacitor plates? What if instead we put a material in between the capacitor plates that allows us to store more charge? That we call a dielectric. Die meaning two, and electric being, well, we store more charge. It is usually an insulating material, like rubber, plastic, wax paper, that's placed between the plates of a capacitor, and it increases capacitance. And dielectric is material dependent. In other words, you should not memorize dielectric constants. You should look them up in a book, like your textbook or an engineering manual or so on. Now, the dielectric constant is often given the symbol kappa. This is the Greek letter kappa, which is a positive constant that's larger than 1. Since that positive constant is larger than 1, the voltage that we can sustain due to a dielectric is going to be basically V0 divided by kappa, so that the voltage times the dielectric constant is this V0. And then notice that the capacitance able to be sustained by a dielectric is kappa times C0. And this is actually probably the more important equation, because if kappa is larger than 1, we have a greater capacitance. So note that the maximum operating voltage decreases. Okay, that's because if kappa is larger than 1, the maximum operating voltage is less, but the capacitance goes up. By the way, kappa is unitless, and the dielectric is usually going to completely fill the region between the plates. Now, in theory, you could take the distance between capacitor plates and make them very small to create a very large capacitance. But in practice, there's sort of a pragmatic, practical limit to D, which is going to exclude electric discharge. In fact, most capacitors that are modern, which are in devices like mobile phones and computer tablets and so on, are very, very small. And the distance between capacitor plates are on the order of micrometers. And it turns out that it's very difficult to disallow a spark or a discharge, because the distance between the plates is so small, because we want to store as much energy as possible, but also be as small and lightweight in our devices as possible. So for a given distance between plates, the maximum voltage that can be applied to a capacitor without causing discharge depends upon the dielectric strength of the material. Okay, so let's take a look at the atomic view of a dielectric. You start off with insulating dipoles that are sort of randomly oriented in that insulating material. Notice that when you put the dielectric between the capacitor plates, the negative sides of the material face the positive plate, and the positive sides of the material pieces that can rotate or adjust face the negative plate. Notice that as a result, we have polarization, and we get a so-called induced electric field that's in the opposite direction of the electric field of the capacitor. As a result, the capacitor can operate by putting more charge on the plates and operating at a larger electric field, because we know that the dielectric is going to allow an induced electric field that overall decreases the operating electric field. So, an external electric field is applied, produces torques on molecules, partially align them with the electric field. An external field can polarize the neutral dielectrics, whether the molecules are polar or nonpolar. And the dielectric acts like a second pair of plates, producing an induced electric field in the direction opposite the original electric field, allowing us to store more charge. Now, in practice, the production of a practical capacitor is shown here. They almost always use a solid or a liquid dielectric. All materials have a maximum electric field they can sustain without breakdown, which is the production of a spark. Now, in air, the breakdown of an electric field is about 3 times 10 to the 6th volts per meter, or newtons per coulomb. Okay, so that's about what, 3 million volts in 1 meter. Okay, so air is not a very good conductor. Okay, it's mostly vacuum. And by the way, a material's maximum sustainable electric field, again, it's called the dielectric strength. Okay, that's listed over here in this table. Okay, so that's the maximum electric field that can be sustained before that spark. Notice that here we have a table of kappa generally going up, and then here a table of the maximum electric field generally going somewhat down, but it's kind of material dependent. Again, you should not memorize these values of kappa. You should look them up in a book. Okay. By the way, I'm not going to really comment about water because it doesn't have a listed dielectric strength, and water we know to be a strong polar molecule, even though it has a dielectric constant of 80. Okay. And again, depending upon the materials you choose, you can get pretty large amounts of additional charge stored via dielectrics. Okay. So that ends this lecture. Thank you very much for your attention, and I will see you in the next video as it relates to capacitor problems. Please like the video, comment if you would want to at the bottom. Please subscribe to the channel, and thank you very much for your attention.